The main rules that we are using are that the derivative of x to a power is equal to n times x to the n minus 1. The derivative of any constant is equal to 0. The derivative of a constant times x is the constant itself. And more generally, if you take the derivative of a constant times any function, you can take the derivative of that function and then multiply the constant back when you're done. So let's use these in a, b, and c here. So starting with the function f of x equals 2x plus 1, the derivative is f prime of x. Okay, that's equal to, well, 2x is referring to this rule here, and the derivative would just be the constant that is in front of it, so 2. We would then add on the derivative of 1, which 1 is a constant, and so its derivative is 0. And that means the answer to part A is that the derivative of 2x plus 1 is just 2. All right, for part B, again, we want to find f prime of x. Okay, the derivative of 25 is 0. Then we're going to subtract the derivative of x, and the derivative of x is just 1. Then we're going to subtract off the derivative of x squared, which means we're referring to this rule here. We'll bring the 2 down front and write 2, copy down the x, and subtract 1 from the exponent. And this is the answer. I think I'll simplify this as the derivative is equal to negative 1 minus 2x. For part C, okay, here we're taking the derivative of negative 30. Negative 30 is just a constant, so the derivative is equal to 0. Technically, in all these questions, we're also using the following fact, that if you're taking the derivative of a sum of two functions, you can just take their derivatives separately and then add them together when you are done. And the same thing holds when you subtract two functions. So basically, if you have something that has 3 or more terms, you can just go through taking the derivatives of each one and then either adding or subtracting them together. For part D, the derivative of f is equal to, all right, we'll start by bringing the 9 down front, and that's 9 over 3, and I know that just simplifies to 3. I copy down the x and I subtract 1 from the exponent. I then subtract off the derivative of, okay, same idea here. I'm going to bring the 80 down front. That's 80 divided by 8, which is 10, times x to the, and if you subtract 1 from the exponent, you get 79. You would then add on 0, and technically you don't have to write the 0 at the end if you want, and this just means that the derivative of this function is 3x to the power of 8 minus 10x to the power of 79. Okay, looking at part E, I think one thing to note for this problem, and maybe I'll look at x to the 20th over 11 first. You could rewrite that as 1/11th times x to the power of 20. That way you can really think of this as bringing the 20 down front. You have this 11 in the denominator, and you'd have 20 over 11. But you're also allowed to leave it in one fraction. Like, that's completely okay. But if it helps, you could rewrite this whole problem like this. Since I expressed it in this form, I'm going to take the derivative from here. So the derivative of f with respect to x is, I'll write this as 20 times x to the 19, and this whole thing is divided by 11. Again, whether you put 20 over 11 in front or leave it as one fraction, it's the same thing. So moving on, if we take the derivative of this part, you'd bring the 7 down front, copy down the x, and subtract 1 from the exponent, and this whole thing is divided by 3. And the last piece will be bring the 3 down front, copy down the x, subtract 1 from the exponent, and divide the whole thing by 2. this is the answer to part E. All right, for part F, okay, let's see, f prime of x is equal to, I'll bring down the 2.5, copy down the x, and if I subtract 1 from the exponent, I get 1.5. All right, next we're going to add on. I'll bring the 3.5 down front and multiply it to the 0.5, and the product of those two numbers is 1.75. I'll copy down the x, and if I subtract 1 from the exponent, I get 2.5. It's completely acceptable to leave your answers like this with an exponent that has decimals, and that's the final answer. For part G, the derivative of f is going to be equal to, right, first we here have pi, and pi is a constant. It is just a number, so its derivative is going to be 0. You'll subtract off the derivative of, I'll bring the 5 down front, copy down the x, and put 4 in the exponent. And so in this case, f prime of x is simply equal to negative 5 times x to the power of 4. Okay, for part H, again, you could really think of this as 1/3 times x plus 4, and maybe even distributing the 1/3 into the parentheses could be helpful, and that would change the problem to 1/3 x plus 4/3. I mean, written this way, it's very easy to see that, okay, 4/3 is a constant, its derivative is 0. Here I have a number times x, and the result will just be the number that is in front of x. So you could write this as the derivative is equal to 1/3, then plus 0, or just, simply the derivative is a third. But you can see that from here as well. You could take the derivative of x, which is 1. You could take the derivative of 4, which is 0. That whole thing would then be divided by 3. It would leave you with 1/3 at the very end. So you could differentiate this thing either way you'd like. For part I, all right, f prime of x is equal to, the derivative of x is 1. I'll add on the derivative of x to the 12th, that is 12x to the power of 11. And then I'm going to subtract off, I'm going to bring down the 3, and I'm going to multiply it to 0.5, and that gives me 1.5 x to the power of 2. For part J, I want to find f prime of x, and the rule that we have where we take the derivative of x to a power, and you get that number times x to the n minus 1, n can be any number. It doesn't just have to be integers or fractions. It also holds for negative numbers as well. So what we have here is we get negative 2, copy down the x, and we subtract 1 from the exponent, and that gives us negative 3. It's completely fine to leave the answer like this, but if you prefer to write it as a fraction, that would be negative 2 in the numerator, and then that would change to a x to the positive 3 in the denominator. So either of these are acceptable. For question 2, we want to differentiate the following expressions, and we want to do it without using the product rule. And the goal is to rewrite the expressions by either like multiplying or dividing or doing some type of algebraic trick. So like here, if you didn't want to use the product rule, what you could do is take this x and multiply it into the parentheses. So what you would have is, we distribute the x to those three terms, and this changes the problem to, we're really taking the derivative of, okay, we'll get x to the power of 4 minus x to the power of 3 plus x. So note, we have not taken the derivative yet. We're just rewriting this function so we can take its derivative without using the product rule. So now, okay, I'll start by taking the derivative of x to the 4th. That gives me 4x cubed minus the derivative of x cubed is 3x squared, and then the derivative of x is just 1, and this is the answer for part A. For part B, same idea. I want to multiply this 4x cubed into the parentheses. So we haven't yet taken the derivative, we're just rewriting the expression. It's going to be 4x cubed minus, okay, then we get 4x to the power of 11, and then minus 4 times x to the power of 8. I'm going to take the derivative of this thing. I get 12x squared minus 44x to the power of 10, and then minus 32 times x to the power of 7. So that would be the answer for this part. For this next one here, there's two ways that you could think about this. You could multiply the 9 to all 4 terms in the parentheses and then take the derivative. There would be absolutely nothing wrong with that. Another approach you can take is noting that if you're taking the derivative of a constant times any function, you can first take the derivative of that function, and then when you're done, you can multiply that constant back. So I'm actually going to use that rule here. You could most certainly distribute the 9 into the parentheses to get the same answer, but my goal is going to be, first, I'm going to take the derivative of this part, and then second, I'm going to multiply the 9 back when I'm done. So I'll do this as my second step. So if I take this approach, okay, I'm going to get 9 times the derivative of 1 plus 2x minus 3x squared plus 4x cubed. Like, this is the way I'm doing it in this order. So that's going to be 9 times. Now, if I take the derivative of what's inside the parentheses, the derivative of 1 is 0, the derivative of 2x is 2, the derivative of negative 3x squared is 6x to the power of 1, and the derivative of 4x cubed is 12x squared. This thing. So I guess we don't really need to write the 0, and we can multiply the 9 into the parentheses if we'd like to, so I think I'll do that next. I'm going to multiply 9 to all 4 terms. I'm not even going to write the first one because I know it is 0. 9 times 2 is 18. 9 times 6 is 54, so we get a negative 54x. And then we have 12 times 9, and that's equal to 108. So I get 108x squared. And this is the answer. So just to reiterate, you could have first multiplied in the 9 and then taken the derivative of that expression, and you will get the same exact answer as what I put here. For part D, I'm going to rewrite this expression as we're taking the derivative of this 1 over x would be better if we wrote it as x to the negative 1. And the reason for that is we can now use this rule for both terms in the parentheses. By taking the derivative, I get negative 1, which I'll put a negative, x to the power of negative 2. Then I get negative 5 times x to the power of negative 6. That is a completely acceptable answer. Of course, you could rewrite this so it was negative 1 over x squared minus 5 over x to the power of 6. Either of these is fine, and that's the answer for this part. I'm going to take the same approach in part E. So again, rewriting this thing as I'm taking the derivative of 1 over x squared is x to the negative 2 minus, okay, we get 4 times x to the negative 5, and then I just leave plus 1 alone. If I take the derivative of this thing, I get negative 2x to the negative 3. I get positive 20x to the negative 6, and then I have plus 0 at the end. Of course, we could rewrite this so the exponents are positive, and it would look like this. And so either of these answers are fine. This one or this one. For this first one, I'm going to rewrite the square roots so they're x to the 1/2 power. They mean the same thing. And the fraction, I'm going to rewrite so there actually is no fraction. So this is the derivative of x to the 1/2 plus 7 times x to the negative 1/2, then plus 1. If I now take the derivative of each piece, for the first one, we get 1/2 times x to the negative 1/2. For the next piece, I'm going to bring down a negative 1/2, so we get negative 1/2 times 7 is 7/2. Then we have x to the, and if you subtract 1 from the exponent, you get negative 3/2. And the derivative of 1 is just 0, and so we have this expression here. If you want to write this so there are no negative exponents, you could write this as 1 over 2 times x to the positive 1/2 minus 7 over x to the positive 3/2, and then we'll multiply this 2 in. And if you'd prefer to use root symbols instead of powers, well, you could also write this as 1 over 2 times the square root of x, then minus, okay, we got 7 over 2 times x to the 3/2 is really the square root of x cubed. So any one of these would be completely acceptable for the answer. So you could write it like this, or even, this would be fine too. For part G, I'm going to rewrite the square root, so it's really x to the 1/2 power. And inside the parentheses, I'm going to write x cubed minus x squared, but then plus x to the negative 1 power. My next step will be to distribute this x to the 1/2 to all three terms. And I'm going to use the rule where I add the exponents because I'm multiplying like bases. So up to this point, I have not taken a derivative. I'm just rewriting the function itself. Okay, so first, if we have x to the 1/2 times x cubed, if I add those exponents, that's really going to be x to the 7/2 power. So 3 is 6/2, and one more gives you 7/2. I then would subtract off, okay, x to the 1/2 times x squared, that's the same thing as x to the 5/2, right? 2 is 4/2, and one more is 5/2. Then we have x to the 1/2 times x to the negative 1, and 1/2 minus 1 is negative 1/2. If I now take the derivative of this thing, for the first piece, I have 7/2 x to the 5/2. Again, I'm thinking of when I subtract 1, I'm subtracting 2/2, that 7 drops down to a 5. All right, minus, okay, I bring the 5/2 down front, copy down the x, and if I subtract 1 from the exponent, I get 3/2. And then the last thing is, I would bring down the minus 1/2, copy down the x, and I subtract 1 from the exponent, which gives me negative 3/2. So this is a completely acceptable answer. But, you could get rid of that negative exponent if you wanted to. So you could really write this as, well, let's see, that's 7/2 x to the 5/2 minus 5/2 times x to the 3/2, and then minus 1 over, okay, that's really 2 times x to the positive 3/2. You could also replace the powers with root symbols. That's totally fine. That would be 7/2, that's really the square root of x to the 5th, minus 5/2, the square root of x cubed, and then minus 1 over 2, and then the square root of x cubed. So any one of these are acceptable for a final answer. For part H, I see I have a fraction here being divided by x squared. I'm going to break this up into 3 separate fractions. So again, we're not taking the derivative to start with, but we are just rewriting the function as 1 over x squared plus x over x squared plus x to the 4th over x squared. These two expressions are equivalent. Of course, you can rewrite this. Okay, this is really the derivative of, okay, you have 1 over x squared, an x over x squared is 1 over x, and an x to the 4th over x squared is x squared. I think writing these so they're not fractions would be a good idea. So this is the derivative of, Okay, that's x to the negative 2 plus x to the negative 1 plus x squared. I can now take the derivative. I get negative 2x to the negative 3 minus x to the negative 2 plus 2x. If you want to get rid of the negative exponents, you could write it like this. Either of these forms are acceptable. All right, so for the next question, I want to use the fact that the derivative of e to the x is e to the x, a function that is its own derivative. Using this, I want to take the derivative of 2e to the x minus x to the 6 plus 10. All right, so the derivative of this thing is going to be, well, the derivative of e to the x is e to the x. So if you have a 2e to the x, you would just multiply by 2 to get this. Next, you'll subtract off. Okay, to take the derivative of x to the 6, you bring the 6 down front, copy down the x, and subtract 1 from the exponent. The derivative of 10 is 0. And so the answer to this part is 2e to the x minus 6x to the power of 5. For part B, I'm going to start by rewriting this function as x to the power of 1/2 plus e to the x. Okay, x over x to the 4th, just here, I know this is 1 over x cubed. Why not write it so it's really minus x to the negative 3? We'll just move that x cubed to the numerator, and then you have minus 8. Everything is written, so I can now take the derivative. I get 1/2 x to the negative 1/2 plus the derivative of e to the x is e to the x. For the next part, we're going to get, well, it's going to be positive because we're subtracting x to the negative 3. So this negative 3 comes down front. It becomes a positive 3. We get x to the negative 4. And then the derivative of 8 is 0. We don't really need to write that plus 0, but we could rewrite this whole thing really as, well, if you don't want a negative exponent, you could put 1 over 2 times x to the positive 1/2 plus e to the x, and then plus 3 over x to the power of positive 4. That'd be fine. Of course, if you didn't want the root symbol, that would be 1 over 2 times the square root of x plus e to the x plus 3 over x to the 4th. So, I meant if you want to include the root symbol instead of the power, you could write your answer like that. These are all equivalent. All right, let's look at part C. Okay, this one's set up directly so we can just take the derivative of each part. So we first get negative 8x to the negative 9 minus the derivative of e to the x is just e to the x, and the derivative of x is just 1. So this thing. Or if you'd like, you could write this as negative 8 over x to the positive 9 minus e to the x plus 1. Those are both equivalent. So either of these answers is fine. All right, so take the derivative of this thing. I actually see you can simplify inside a little bit. 10e to the x minus 11e to the x. Well, I mean, really, that's just the same thing as the derivative of, well, 10 minus 11 is negative 1. So I'll just put negative e to the x. And then we have plus 2 to the power of 4. So if I'm taking the derivative of this thing, the derivative of negative e to the x is negative e to the x, plus the derivative of whatever 2 to the power of 4 is. And 2 to the power of 4 is actually just a constant. There is no x anywhere within this expression. Its derivative is 0, meaning the entire answer is just negative e to the x, like this. It'd be a mistake to say, oh, I want to take the derivative of 2 to the power of 4. Well, that's going to be 4 times 2, and then you subtract 1 from the exponent and get 3. Like, that might seem like something you want to do, but no, that is no good. Don't do this. And that's only because 2 to the power of 4 is a constant. So its derivative is 0. All right, so here we have a graph of x squared minus 10x plus 21. I want to find f prime of x and then use that to determine where the derivative is 0, negative, and positive. Now, I think we're going to be able to answer these without even taking the derivative. And I'll start by saying, well, where's the derivative equal to 0? That is definitely this spot right here. Here your graph is decreasing. Here your graph is increasing. But for this one instant, your graph is level. That means it has a slope of 0 for its tangent line. So I already know the answer to this part. It has got to be x is equal to 5. So I'm just going to make a note of that above here. Like that's got to be the solution. Also, I know where the derivative is negative. That's wherever your function is decreasing. If your function's moving downward, you're basically saying it has a negative slope. And the slope is determined by your derivative. So I know the answer to this part would have to be, well, the derivative is negative when we are less than 5. Likewise, here the function is increasing. That means at any point that you pick, it has a positive slope. Where is your derivative positive? It's going to be where the graph is increasing. And so I'll just note that, okay, it's got to be x is greater than 5. So we know the answer. I just want to verify this by taking the derivative and then solving where it's equal to 0 and thinking about where it's negative and positive. So let's see. I need f prime of x. That's going to be 2x minus 10. If you want to know where your derivative is equal to 0, you can solve this equation. You would add 10 to both sides. You would then divide both sides by 2. And hey, what do you know? You get that x is equal to 5. That is precisely what we thought, just by looking at the graph itself. If you want to figure out where your derivative is negative, you could actually take the formula for the derivative, which is 2x minus 10, and ask the question of, well, where's it less than 0? The process of getting x by itself will be identical to what we did here. You would add 10 to both sides. You would divide both sides by 2. Neither of those steps are going to change the direction of the inequality. It'll definitely result in the fact that x is less than 5. This is where your derivative is less than 0, right here. This is where it was equal to 0. If you wanted to know where your derivative was greater than 0, same idea. You would say this is the derivative. Where's it positive? After adding 10 and dividing both sides by 2, you would have that x is greater than 5. I think I'll add one thing onto here. You can actually graph the derivative. It's an equation that you can graph in the xy plane. Here's the original function. If you want to graph the derivative, it's a linear equation. It's 2x minus 10. I know it's equal to 0 at 5, so you could, plot the point 0 here. I know it has slope 2, which means it goes over 1 and up 2. You could, keep plotting points like that in both directions. But this thing is the graph of the derivative. This is f prime of x. The important connection is that this is where your derivative is positive. It's easy to see because it's above the x-axis. And wherever your derivative is positive, your original function is increasing. Here your derivative is 0, and it refers to this horizontal spot on the original function. Here, your derivative is negative, meaning it's below the x-axis, and that's where your original function was decreasing. It is sometimes useful to actually graph the original function and the derivative itself to see the connection between these ideas, where it's 0, where the derivative is positive, and where your derivative is negative. For question 5, we're again given this function, it's here. I want to figure out from the derivative, where is it 0? from the graph or the derivative, where is it negative, where is it positive? This is set up so I think I can look at the graph and just know the answers ahead of time, and then we'll just verify our work by looking at the derivative. So where is the derivative equal to 0? I mean, it looks like there's two places. Maybe here and here. It kind of looks like the answers are 2, but also 5. All right, where is your derivative negative? That's going to be wherever your function is decreasing. And the function is decreasing here as we go from x equals 2 to x equals 5. The graph starts moving downward. Everywhere else, your function is increasing. So I think the answer here is everything between 2 and 5. Where is your derivative positive? That's going to be where the function is increasing. And it looks like we have two pieces for that. Anything that is greater than 5, so I'll put greater than 5, but also anything that is less than 2. So maybe I'll just like put, or x is less than 2. Let's verify this. Okay, step 1. What is the formula for the derivative? Okay, looking here, it's going to be 6x squared minus 42x plus 60. That thing. And if you want to know where it is equal to 0, I can set this equation to 0 and solve for x. I'm noticing that every term is divisible by 6, so I'm going to divide both sides by 6. So here I'm saying, I can just take this whole side and this whole side, divide it by 6, simplifying my equation to really x squared minus 7x plus 10 equals 0. This factors. I have an x and an x. They both have to be negative to multiply to a positive 10. It's got to be 5 and 2. The product of those two numbers is positive 10, and the sum is negative 7. This means that the two numbers that make the derivative equal 0 are, no surprise, 5 and 2. You put these two numbers into this equation, your derivative becomes 0, and that's referring to the place where your original function is horizontal. Now, in terms of, where is the derivative negative? We already saw this. I'll write it as an interval, but that's from 2 to 5. Or you could write, 2 less than x less than 5. I can actually see that on the graph. That's where the function is decreasing. And like we said before, where is your derivative positive? You could also write this as an interval. It's whenever you're less than 2, or, which I'll use a union symbol, and say when you're greater than 5. But what I'm going to do is on this graph, I'm going to look at this function here. So I'm going to plot that. All right, so I did this in Desmos. It's not going to be like a perfect sketch, but I see a quadratic kind of like comes down like this. It goes through this point and drops down a little bit, and then it kind of comes back up like this. Not a perfect sketch, but this is the derivative. That is this equation that I plotted along with the original graph. And what I'm noticing is where your derivative is 0, we get these two horizontal parts on the original function. Okay, here your derivative is negative because it's below this axis. So it is negative numbers, and that means your original graph is decreasing. Here, the derivative is positive, and that means your function is increasing. Here, the derivative is also positive, and that corresponds to where the function is increasing as well. So this all matches up if I compare the two functions, the derivative and the original graph itself. So given this function, represented by this graph, where's the derivative 0, negative, and positive? It looks like it is 0 at two places. I'm going to mark those. Looks like that's here and here. So perhaps the x values are it looks like -4 and also +6. Now, where is your derivative negative? That's going to be wherever the graph is decreasing. So it looks like if you're less than -4, your derivative is negative, but also if you're greater than +6 for x. So that is, it's negative if we are less than -4 or if we're greater than 6. Where is it positive? That should be where your function is increasing. That looks like it's between -4 and +6. Just guesses up to this point. I'm going to try to verify this by taking the derivative and setting it equal to 0. Okay, so the derivative of this function is, okay, we get -6x squared plus 12x plus 144. Where is this thing equal to 0? Okay, we can solve that. And okay, I think I can divide 6 into, well, in fact, -6, I think I can divide into all of those terms. So I'll divide both sides by -6. And when I do that, I get positive x squared minus 2x, and then 144 divided by 6 is -24. I think this factors. We'd have to have an x and an x. One has to be positive, the other has to be negative. I think it'll be -6 and +4. Those multiply to -24, you add to a -2. And that means the two solutions are where each individual factor is equal to 0. One is at -4, and the other is at +6. Again, no surprise. I can actually see those two locations on the graph itself. So in terms of, where is the derivative negative, we've determined that too. That's this part of the graph and this part of the graph. I'll write it as intervals, but that's from -infinity to -4, and also everything from 6 to infinity. Where is the derivative positive? That's where your original function is increasing. That's between -4 and +6. I think for this problem, I'm also going to graph the derivative in the same xy plane. All right, I did this in Desmos. I didn't get like a perfect picture. I'll just try to sketch what I'm seeing here. I can see that the graph definitely equals 0 at these two places. I really had to adjust the x scale and y scale so I could see a decent picture. But the graph kind of like came up like this, didn't go too far up, and then comes back down through that point here. So like this is what I get when I actually graph the derivative. And that matches up with the slopes on this original graph. Here, your derivative is positive, meaning it is above the x-axis. A positive derivative means your original function must be increasing. Likewise, here your derivative is negative. That means the original graph itself must be decreasing. Here, the derivative is also negative, and the graph is also decreasing at those corresponding x values. So we actually used an equation to figure out where the derivative was 0, and it matched up with the original picture, and then I used a graph to figure out the rest of these parts here. Here with the graph of a cubic equation, I want to find the derivative, determine where it's 0, negative, and positive. If I look at this graph, it looks like the function is always increasing, except for maybe around here. Like it looks like it's moving up, and then it levels off to maybe become horizontal at this one point, and then it keeps moving up again. So in terms of where the derivative is 0, if I were to guess off of the picture, it kind of looks like it's only at -4. It looks like it's just at this one spot. Again, that's just a guess. We can try to verify this later. But where is it less than 0? I don't see anywhere where the graph is moving downward. So less than 0, it kind of looks like nowhere. which is possible. Therefore, where's the derivative positive? That's got to be every place except -4. So maybe I could write that as, my guess is every number except at -4 where the derivative becomes 0 for an instant. That's just a guess at this point. So what I'm going to do is take the derivative of the original function and try to set it equal to 0. F prime of x, okay, that's equal to 3x squared plus 24x plus 48. And I want to know, where is this equation equal to 0? I think 3 goes into every single term, so I guess I could divide both sides by 3. So I'll divide by 3, divide by 3. Let's see, that gives me x squared, 24 divided by 3, that's 8. And then that must mean that if I divide 48 by 3, yeah, it doubles. I get 16. Okay. You could, try factoring this thing using the quadratic formula, whatever you want. I just happen to recognize this thing as a perfect square. You'd have x and an x, everything has to be positive. 4 and 4 multiply to 16, yet also add to 8. This is equivalent to x plus 4 squared is equal to 0. Let me fix that. What is going on there? There we go. Okay, that means if you set both of these factors equal to 0, you get the same number. There aren't two different solutions. They both happen to be, well, if you let x plus 4 equal 0, you get x is equal to -4. There is only one number where the derivative equals 0, and it's right here. Everywhere else, the derivative must be positive, and it's never negative. It's never below the x-axis. So what I'm going to do is take this derivative, I'm going to graph it on this plane just to see what it looks like. Okay, I graphed the function in Desmos. I don't have like a perfect picture of it, but it definitely equals 0 here. It drops down, it goes to this spot, and then it bounces right back up. So, not a perfect sketch, but I see something that looks like this in Desmos. I mean, this is perfect. This perfectly matches up. The derivative is 0 at one place, and I can see that on the graph itself. Now, the derivative is decreasing, but who cares? I mean, this is positive. The derivative is positive, and that means your original function is increasing. Again, here, now the derivative is increasing, but that doesn't matter. It's positive. It's above the x-axis, and that means your slopes are positive, and the graph is increasing. Everything matches up here. This is where the derivative is equal to 0, and it's negative nowhere. And every place where the derivative is positive, so, where is the derivative greater than 0, it's all x's except -4. As an interval, you could write it like this, from -infinity to -4, and then union -4 to infinity. All right, for question 8, here we have the graph of a linear equation, 2x minus 3, so this thing right here. Where's the derivative 0, where is it negative, and where is it positive? I don't see any place where the derivative is equal to 0. I mean, clearly this graph is always increasing. It's never decreasing, and it's never horizontal. It's always moving up. So where's the derivative 0? I'm thinking it's not. So I'll just put, nowhere. Where's the derivative negative? This graph is never decreasing, so, I mean, it looks like it's nowhere for it's equal to 0, but also where is it less than 0? Now, where's the derivative positive? That looks like everywhere. And that's because your graph is moving upward, always. A graph that moves up means the derivative must be positive. I think this will be very easy to verify, but let's just do it by taking the derivative of 2x minus 3. The derivative is, well, 2x goes to 2. The derivative of 3 goes to 0, and really I would just write that the derivative is equal to 2. Okay, I mean, I think this completely answers this question. If you set the derivative equal to 0, you'd be solving this equations, but there are no solutions. So that means the derivative cannot be 0. But that shows up in the graph. The graph is always moving upward. It's never level. Where's the derivative less than 0? Again, no solutions. You'd be trying to solve where's 2 less than 0, but that doesn't work. Where is the derivative greater than 0? Everywhere. And that's because 2, the derivative, is greater than 0. So that answers this problem. The derivative is greater than 0 on the entire real line because it is always equal to 2. If you want to graph the derivative, if you graph the function 2, it is this horizontal line. Your derivative is always positive, and that means your graph is always moving upward. In question 9, we're going to use the product rule if we ever encounter a product of two functions. The product rule says that you take the derivative of the first, and then you multiply by the second function, and then you add on, you leave the first function alone, but multiply by the derivative of the second. So if I look at part A, I have two functions, x to the fifth and e to the x. If I want to take the derivative of this thing, I'll just note that x to the fifth is the first thing, and then e to the x is the second. So here is the derivative. You would first take the derivative of x to the fifth, which is 5x to the fourth, and then you just copy down the second function, which is e to the x. You then add on. Now you leave the first thing alone and take the derivative of the second. Just so happens that the derivative of e to the x is e to the x. And this is the final answer for this part. You could factor things out if you want to, but I'm going to leave it just like this. Same idea for part B. I see that there is a product of two functions. We have x to the fifth, but we also have e to the x plus 10. You could multiply in this x to the fifth, but I think I'm going to just use these two pieces as my product. So the answer is you take the derivative of x to the fifth, which is 5x to the fourth, and then you just copy down the second piece. You then add on. All right, now you leave the first thing alone, which is x to the fifth, and then you multiply by the derivative of the second piece, which is e to the x plus 0, because the derivative of 10 is 0. And you can simplify this, but I'm going to leave my answer just like this. For part C, I'm going to rewrite the function itself before I take the derivative. It's 2x e to the x. It's minus 1, but x times x cubed is a product, but you could just write that as x to the fourth instead of using the product rule to take its derivative. Let's see what we get. I'll note that for the first piece, I have a product of two functions, so I'm going to use the product rule. If I take the derivative of the first, I get 2. If I leave the second thing alone, that is e to the x. I then add on. Okay, now I leave the first function alone, which is 2 to the x, and I multiply by the derivative of the second, which is e to the x. I took the derivative of this first part. I now move on to this minus 1. Minus 1 has a derivative of 0. The last part is taking the derivative of x to the fourth. That is 4x cubed. So I guess as a final answer, I put 2 e to the x plus 2x times e to the x plus 4x cubed. This is the derivative of the original function. I think I'm going to do a similar thing for the next part. Again, I have a product of two functions. So instead of distributing the e to the x, I'm going to start by just applying the product rule. Product rule says you take the derivative of the first piece, and the derivative of e to the x is actually just e to the x. And then you just copy down the entire second function. You then add on. Okay, you don't do anything to the first function, but now you multiply by the derivative of the second part. The derivative of 1 is 0. Then we have minus the derivative of x to the fourth is 4x cubed. And then the derivative of 5x to the seventh is 35 x to the power of 6. This thing. And I think there is a lot that could be simplified here. You don't have to write this 0. You could factor out an e to the x, and then you'd have like one polynomial left over. I think it's worth me writing that out, so I think I'll do that. So for starters, if I take e to the x out from both terms, so I remove this and I remove this, you won't need either sets of parentheses anymore, and you can simply just copy down every single term that remains, and I'll exclude this 0. So we'll have 1. Okay, we get a minus 4x cubed. We get a negative x to the fourth, a positive 35x to the sixth, and then plus 5x to the seventh. So I suppose you could write the answer like this if you wanted to, but the goal here is really just to take the derivative, and this first part would be okay as well. To take the derivative of e to the x times e to the x, using the product rule, we would have the following. Okay, for that first e to the x, you would take its derivative, and you do get e to the x, and then for the second e to the x, you would leave that alone, and so you just get e to the x. To complete the product rule, you then add on. You leave the first thing alone, but take the derivative of the second, which is actually also just e to the x, and you get this thing. And, those two things are the same. You're saying you have 2 e to the x times e to the x. And because we have like bases, we can add the exponents, which you could really just write as this, 2e to the 2x. What is going on in this example? We have e to the x times e to the x times e to the x. And we didn't really have a product rule that said what to do if you have 3 things in the product. But the way around this is to, okay, you could start by leaving the first thing alone, and then treat the last 2 parts as one function. All right, let's, try to work through this one. I think it's worth noting that in the previous part, we already took the derivative of e to the x times e to the x, and we got 2e to the 2x. I'm going to use this when working through this problem. So make sure that you go to the previous part if you want to know why this is true. Anyway, picking up, if I'm using the product rule here, the product rule says to first take the derivative of the first piece, and so that would just be e to the x. And then the product rule says, now just copy down the second function, don't take its derivative. You then would add on, okay, you leave the first thing alone, but then you multiply by the derivative of the second function, which we already did in the previous part. So I'm just going to put that here. This is it. This is the derivative. I think it is definitely worth simplifying this thing. These bases are the same, and that means we can add the exponents. This is e to the x plus x plus x, right? I mean, really, you have 3 x's in the exponent. And over here, we're multiplying 3 things together. I'll put the 2 out front, so maybe I should have written that first. I'll put a 2 here. We have e to the x times e to the 2x. The bases are the same, and that means we can add the exponents together, which are x plus 2x. Here it is. Oh, right. I can re-express this as, well, that's really e to the 3x plus 2e to the 3x. And, the answer is really you have 3 e to the 3 x's. So that is the completely simplified answer to this problem. And if you want to think about this, which you don't have to, it does appear that there is something emerging. Like if we have e to the x times e to the x, that's 2e to the 2x. If you have 3 of them in a row, you'd have 3e to the 3x. I wonder if this holds. I'm just sort of asking, it's not necessary for this. But if you had e to the x times e to the x times e to the x times e to the x, would the derivative of that thing be 4e to the 4x? That's worth thinking about. So if you want to try it, go for it, but not required. In question 10, we're going to need to use the quotient rule, which tells us how do you take the derivative of a function f of x divided by a function g of x. The formula is this. It looks a lot like the product rule where you'd have f prime of x times g of x, but then we encounter our first difference. You don't add, but you subtract, and then you reverse the situation where you leave the top function alone but multiply by the derivative of the bottom. Furthermore, you get another quotient as your answer, and in the denominator is g of x all squared. So the quotient rule resembles the product rule a lot, but you are subtracting instead of adding. So the order in which you apply this matters, but you also get this fraction, and in your denominator is the square of this denominator. Let's apply this rule to this problem here, just to see what it looks like. The top function is x plus 1, and the bottom function is x minus 4. The quotient rule says that you take the derivative of the top. I'll put it in parentheses, but the derivative of x plus 1 is just 1. It's the number that's in front of this x, and that 1 goes to 0. Then we just copy down the denominator and write x minus 4. You then subtract off the top, which is x plus 1, and you multiply by the derivative of the denominator, and the derivative of the denominator is also 1. And you divide this whole thing by the denominator squared. In general, when encountering the quotient rule, it is often good just to leave this denominator as squared instead of multiplying it out. So it's customary just to leave your answer in the denominator like this. However, if you can simplify things in the numerator, that's worth doing, so we should try that. So this answer, it is acceptable. There's nothing wrong with this. But if you want some practice simplifying it, okay, the numerator is really x minus 4, and then this 1 is unnecessary, and I can distribute this negative to both of these terms, and so you get minus x minus 1 all over x minus 4 squared. X minus x is 0, negative 4 minus 1 is negative 5. This is how the simplified answer would look. You would leave the denominator as something squared, but you can simplify the numerator of the fraction nicely. Before doing part B, I wrote down like the shorthand version of the quotient rule. I just left off the parentheses and x's, just to indicate that you take the derivative of the top, multiply by the bottom, subtract off the top times the derivative of the bottom, and then you divide by the denominator squared. Okay, taking the derivative of this thing, the quotient rule says to first take the derivative of the top, and that would be 2x plus 1. And then you multiply by the denominator. And that just means you leave it alone, and you get this thing. Next, you leave the top alone, which is x squared plus x plus 1, but now you multiply by the derivative of the denominator, which is e to the x. And this whole thing is divided by the denominator squared, which is e to the x plus 1 squared. And really, this is acceptable in terms of just taking the derivative of an expression. I think I'll actually go through the process of multiplying everything out just to see what this thing becomes. All right, so it's going to be this giant fraction. That'll be fun. All right, let's see. We get 2x times e to the x. That is 2x e to the x. We then have 2x times this 1. That is plus 2x. It's great. Okay, then I multiply in this 1, so I get e to the x and another 1. So I'll put plus e to the x plus 1. Now over here, I'm going to multiply this e to the x to these 3 terms. And then note that this negative is just going to make all of those terms negative themselves. So the first thing I get is negative e to the x times x squared, which I'll put x squared e to the x. I then get negative e to the x times x. I'll just put x e to the x. And then I get e to the x times this 1, which is e to the x, and it is also negative. And the denominator is still e to the x plus 1 all squared. Now, was this worth it? Does anything actually cancel within the numerator? And a couple of things can be combined. I have a e to the x and a negative e to the x. Those are gone. What else do I have? I have a 2x e to the x and a minus x e to the x. So I can combine this term and this term. So let's start doing that. Okay, we get, when I combine this and this, I'm subtracting one of those from one of these. So I have an x e to the x. Okay. So now I have 2x. That's not going to combine with anything. So I'll just put plus 2x. I have a 1, which also does not combine with anything. So I'll put plus 1. And then I have minus x squared e to the x, and that doesn't combine with anything either. And that's divided by e to the x plus 1 all squared. That's as far as I'm going to take this. It doesn't seem like anything else cancels or combines. This is fine for an answer since we're just taking the derivative, but if you feel like it, you could write it like this as well. Okay, so for this problem, I'm going to take the derivative of the numerator, which is negative 4x cubed, and then multiply by the denominator, which is 1 plus x to the 4th. I'll then subtract off the numerator times the derivative of the denominator, which is 4x cubed. And this whole thing is divided by 1 plus x to the 4th, and that whole thing squared. This is a completely acceptable answer. However, I am going to simplify it just to see if it makes it look any better. I'm going to multiply in these terms and then see if anything cancels. So we're going to have a giant fraction. All right, if I multiply in a negative 4x cubed, I get another negative 4x cubed, but then I get a negative 4x to the 7th. Now over here, when I multiply in this positive 4x cubed, I know what I'm going to get, and this negative will change the sign on those two things. So from here to here, I get a positive 4x cubed, but it really becomes negative. So I get negative 4x cubed. Then I get a negative 4x to the 7th, but it becomes positive. It still is divided by 1 plus x to the 4th, all squared. Some stuff does cancel. This negative 4x to the 7th and this positive 4x to the 7th. These are like terms, so I can combine their coefficients. And that gives me negative 8x cubed all over 1 plus x to the 4th squared. And this is the simplified answer, but since we're just taking derivatives, this is completely okay too. To use the quotient rule in this one, I'm going to start by taking the derivative of the numerator, which is 2x plus 1, and then I multiply by the denominator, which is x cubed plus x squared plus x plus 1. I subtract off the numerator, which is x squared plus x plus 1, times the derivative of the denominator, which is 3x squared plus 2x plus 1. And this whole thing is divided by x cubed plus x squared plus x plus 1 all squared. And that's it. that technically is the final answer to this problem. Is it worth simplifying this thing? I really don't know. I think it's going to take a long time. Oh, why not? All right, so I'm going to try to write this thing out. Let's see what we get here. It's going to be an enormous numerator. I think I'll have to write it in like several lines. I'm going to multiply this 2x to those 4 terms, and then this 1. I'll do the same or a similar thing over here, and I'm going to note that everything over here is going to become negative. Starting with this 2x, we get 2x to the 4th plus 2x squared. Nope, already made a mistake. Plus 2x cubed plus 2x squared plus 2x. Multiplying in the 1, we get plus x cubed plus x squared plus x plus 1. Fantastic. Okay, then you would subtract off, and then everything that would appear from the multiplication of these two expressions, it'll all be negative. Okay, so I'm going to multiply in this x squared. We get 3x to the 4th. We get plus 2x cubed. And then we get plus x squared. If I now multiply in the x, I get a 3x cubed. And then we get a 2x squared. And then we get a plus x. All right, great. And then if you multiply in the 1, you get 3x squared plus 2x plus 1. That thing that I just wrote is supposed to represent my numerator. And that whole thing is being divided by x cubed plus x squared plus x plus 1 all squared. All right, let's see if we can see what combines and what cancels. So I'm going to combine terms and write it in red over here just to see what it looks like. Okay, we have a 2x to the 4th, and that's all by itself. So I'm looking at this stuff. I have a 3x cubed. I have a 3x squared. I have a 3x and a 1. Okay, and then if I look at all of this stuff, I can erase this. I don't really need that. If I combine all of the stuff from my second term, okay, we get a 3x to the 4th. Right, great. We get a 5x cubed. We get a 6x squared. We get a 3x and a 1. And this stuff is being subtracted from this stuff. So I'm just going to write down what is left over. Okay, when I do, 2x to the 4th minus 3x to the 4th is a negative x to the 4th. A 3x to the power of 3 minus a 5x to the power of 3 is a negative 2x to the power of 3. 3x squared minus 6x squared is negative 3x squared. 3x minus 3x is 0, and 1 minus 1 is also 0. So this whole thing is now just being divided by x cubed plus x squared plus x plus 1 all squared. I don't know. I honestly don't know if that was worth it. But there it is. This answer up here, I think for what we're doing is good enough. And that is it.